Hello, welcome everyone to the Supergen Offshore Renewable Energy Hub webinar series. My name is Philip Thies. I'm a professor of renewable energy at the University of Exeter and also one of the co-directors of the hub. I've got with me Ed McKay, who also works on the project. Ed, do you want to briefly introduce you?
Hi everyone. Yes, my name's Ed McKay. I'm a researcher on the Supergen project. I'm working on some of the experimental tests and theoretical modelling of the dynamic power cables. So be happy to answer any questions as we go along or at the end.
Thanks, Ed. Which brings me to kind of the format. So this is the fourth webinar we've been running. Some of you may have been to previous ones. There'll be another one in July, so there's a little summer break. With the colleagues in Edinburgh on the policy topic, so you can sign up to those via the website. In terms of this webinar here, so I'll be talking about the physical testing of dynamic power cables, which we believe is the critical link. In terms of kind of communications during and after the webinar. So you're able during the webinar, so while I speak, basically to put questions in the chat, and Lee and Kirsty from the team will kind of see those questions coming in and then forward them on to me and Ed. And then at the end, we should have some time for discussions as well, so we can have you can put your hands up and actually speak rather than just type it in. But either of those works. So if you have any burning questions during the slides, please do feel free to put them in the chat. So the talk on physical testing of dynamic power cables, as the title says, very much focuses on the physical side of the testing. Power cables obviously tested both electrically and physically. Much of the focus, I guess quite naturally, on the cables is on the electrical testing. This talk is only on the mechanical and the physical testing of those cables. So that's just an important kind of distinction at the beginning. I'll talk a little bit kind of around, because I recognize not everyone is here with a cable background. So I've got some introductory slides on kind of what is the challenge, why do we think this is an issue, and kind of some of the approach that we've taken to model things like cables for floating offshore wind turbines, and then to do the physical testing. And then I've brought a number of case studies, really, the ones I can talk about on dynamic testing. So cable on its own, cable and the bend restrictor, and the cable and the bend stiffness, so some of the ancillary systems as well. And then, as I said, at the end, we should have some time for discussion and summary. What is important, and I think that's what I'm saying, I'll bring the things I can talk about. A lot of these things are kind of under confidentiality clauses. There's not actually very much literature on some of those topics out in the open domain. So as part of the Supergen project as well, we're working around some of those caveats to be testing real cables, but then obviously we have to protect any interests. The projects I can kind of present, they were all in one way or the other publicly funded, and one of the stipulations there is, of course, they have to be accessible to the wider community. So why are kind of cables an issue? Well, they fail a lot, and when they do, it's very costly. So some of the statistics from the insurance side would suggest that almost 80% of the insurance claims is in some way or the other related to cable failures. Again, from a reliability point of view, and kind of my area, there's not that much published data. So one of the few studies that's publicly available is by Warnock and all colleagues from 2019 that kind of surveyed or had access to data for a range of offshore fixed wind cable installations, and you can see kind of the different farms do varyingly good or bad. On the y-axis there, you see the failures per kilometer per year. So that's kind of the average for those different farms, and you can see some of them are above, some of them are below the average, but the average kind of failure rates comes in at about 3 failures for every 1,000 kilometers of cable per year, which is quite high, really. And that's for kind of fixed installations. So we're not even out at the the floating wind with very dynamic configurations. So it's really the cost of those failures. And a lot of the times we've been manufacturing cables, or the industry has been manufacturing cables for a number of years, but in some respects, installing that, and I have some examples, installing that, say with a fixed or even with a floating wind turbine, is a new application. So by definition, if that engineering design isn't matured enough, you'll have some failure modes and some failure mechanisms that you'll experience in the field. So the point of the testing really is to do some of that in the stages before, in the testing ahead of field installation. This is kind of an introductory slide just to put into context a little bit, and kind of what are those cables, how they actually look. So if you'd install a cable and connect it to a floating wind turbine, for example, here, these are kind of typical configurations. So this one's called a lazy wave configuration. And obviously the yellow part, try and find a pointer. I'm not sure, I hope you see my my mouse. So you have the cable here running along, and some of the ancillaries at the top. You have the hang off at the bend stiffener. Got the buoyancy modules creating the lift. And then you have a touchdown point. This part here is called the dynamic power cable, because that's the part that crosses the water column. For fixed wind, that doesn't really exist. So you exit the J tube or the monopile, and then basically become a static power cable along the seabed. In either case, the cable is a key component of your installation, because if you generate electricity and you export that electricity, you obviously rely on the cable as your main line for electricity transmission. If that fails, you won't have a revenue, and if you haven't got a revenue, your project obviously is in trouble. So you really rely on those cables to have high integrity and high reliability. I'll have another slide on cables, but just to kind of highlight this, they're treated as component, but they're really very heterogeneous structures. They have a complex kind of inside, and that really is the difficulty in some of the testing and figuring out the failure mechanisms. In terms of context for the SuperGen Offshore Renewable Energy Hub, the cables sit in kind of what we call work stream, so it's work stream 4, and what we're trying to do really overall is to have real cables and make a contribution in better characterizing their mechanical properties. So in a lot of the modeling that we do, simplified assumptions, and I'll show you some of the things. If you do physical testing, how you can actually get a better characterization of the cable. In an attempt, coupled to some of the numerical modeling, to produce some reduced order models that then can be used in some of the hydrodynamic softwares. And at the end of the project, we're hoping to have a set of reference cables or a set of reference cable designs that can be used by kind of interested parties to basically model the cable behavior in a bit more detail than we currently do. Different cable types. Again, that's just to get an idea of what the size and the dimensions of these. So you generally distinguish, well, it's high voltage alternating current, so AC cables on the left here, and then you've got your DCs on the right. So that's basically how many cores have you got. So for the HVDCs, you've got single core, and for the AC cables, you obviously have 3 cores. In terms of the diameters, it depends a little bit where you are. So if you're inside, so we're talking offshore fixed wind, if you're inside the array, so the inter-array cable has a smaller diameter, typically around the 110 to 160 millimeter outer diameter. And you see some of the ratings there. In terms of what they can sustain, the minimum bend radius is really important. So those inter-array cables can do 2 meters, can go down to 2 meters. With those specifications. And then you've got the export cable that basically, once you've collected all the electricity you have from the substation going out, you see much larger diameters there, 250 to 320 millimeters. And therefore the minimum bending radius goes up as well to about 5 meters. And then you see the HVDC cables, they become smaller, one of the reasons you do those. And then you have much higher voltages, but that's just an idea to get a bit of representation of size and dimensions. The middle picture there gives you an idea of what I meant to, that they're actually composites, if you like. They're heterogeneous structures, lots of layers. You've got the core inside. Outside, around the core, or the conductor core, you then got a conductor shield, buffered by the insulation, buffered by the metallic sheath, and then you've got another typically plastic sheath. Some filling and kind of profiles to keep those things in place. The fiber optics are also part of the cable, and then kind of if you go further to the outside, you've got basically tapes to hold it all together to then be able to do the outer armoring and the outer sheathing. So what you see here in the middle is a single armored cable. Some of the heavier and more dynamic ones would have 2 or sometimes even 3 armor layers. So you can adopt any of those layers. But the understanding really is you build those up out of layers, and they interact with each other. So it's not as straightforward to say which of those layers is now going to fail. Which kind of leads me to the coupled modeling, because so for floating wind, and that's a lot of the research that we do, there's a number of existing models, and some of you might well be using those for the different floating wind types, and kind of we have a good understanding of different mooring systems and what the load cases are, and the cable then has to be designed in, and a lot of the times the cable is then kind of added onto it. But our belief is that you actually need an integrated design between the moorings and the cable, because one relies on the other. So things like the minimum bending radius, if you have to sustain that, you have to design a mooring system that protects your cable in a way. And the challenge is for those kind of coupled models, what are the properties that you assume for the cable? And then you basically need an iteration between modeling the loads and making sure that the cable survives both the extreme conditions and the fatigue limit states over a longer duration of time. And that problem exists not just in the offshore sector, that exists in the aviation industry, it exists in automotive components. So looking at some of those, that's quite a while ago now, so you can see how long we've kind of been thinking about these things. But one of the processes is to have what's called a service simulation testing approach, where you think about the operating profiles of any sites you're going to and any load measurements or field installations ideally that you have, but those could be hydrodynamic and kind of numerical models as well, or tank tests. So any type of load measurements and load response will help. And if you can measure those either in the field or capture them numerically, you can look at the different operating profiles and basically identify load segments that cause you fatigue damage over time, and you can kind of collect them up and sequence them in a service simulation test, so that you have a physical test of what you think that cable or the mooring system, if you're testing other systems, what those components would have to withstand in the field. So you're trying to replicate that as much as possible before you go out to site. And we've done kind of that kind of mixture of a combined physical and numerical model for moorings, and we're now going to do that for cables as well. So we had some novel mooring components that had you can see here, kind of non-linear behavior. And what we've done is we measured that physically to not just rely on kind of the engineering models to say what the behavior of that component is, but to have a real measurement. And then we could use that measurement in a numerical model to then get a better understanding of how does that affect the kind of the overall load response of the platform. That's less likely to be the case in the cable. So the assumption generally is that what you do to the cable isn't affecting the platform. So it's much more the other way around. What you do to the platform will affect the cable, or what you do to the mooring system will affect the cable. But nevertheless, if you have the actual physical properties and the stiffnesses of the cable correct in your numerical model, you get a better understanding of what are the actual stresses, or more accurate, what are the stresses that the cable is likely to or what does it have to withstand? So in terms of the cable, it would look something like this, and this is what we're partly trying to do. So you have a global model, say for floating wind turbines, where you model the interaction between the environment, your platform, that's obviously coupled to the mooring system as well, and the effect on the cable. That's the entire cable along its length. So you're getting motions and loads on those cables. And then for each of those nodes, what you typically have to do is a 2D model, and there's a couple of software codes that do that, where you then do the cross-section analysis to see what's the effects on the individual layers. And we've done a little bit of work to extend that into the 3D domain, which becomes computationally quite expensive, but gives a bit more information on how the kind of the helical lay affects the cable along one pitch length. And then on the physical testing, I say you want to do, well, there's electrical testing, and then we very much focus on the mechanical testing of those cables to see what is the actual load response, and how does that correspond to the numerical models, which we can then update with some of those results. And we've done that, so there's a couple of different test rigs. So we've got one test rig at the University of Exeter, which we call the Dynamic Marine Component Test Rig. This is kind of an overview of that. So what we're having is at the far end, so closer to you here, is what we call the moving headstock, and we can basically pivot those two axes in and out to replicate what we think are the bending moments and the angles that the cable will see. And at the same time, at the far end, what we call the linear headstock, or the linear actuator, excuse me, we can apply a tensile load. So it's effectively a hydraulic test machine where we can run either forces or displacements on the components. So the idea is not to represent the entire cable, but we take a section, say near the hang-off point or near the bend stiffener, where it's likely that where the cable sees the highest stresses, and we can then run those either field measurements or numerical loads back on the rig to see what the cable response is. That's where technology will be put to the test. So I've got a video here just to show you one of the time series, and I hope that shows for you. So we basically have to program the rig for any test campaign that we do. And that could be either cyclic modes or actual time series. So this time series here is coming out of a numerical model, and it's simulating the point just below a bend stiffener to see what the actual cable response is. And you can see kind of the extent of the motions that we can achieve. And at the far end, we kind of control the tensile load on the cable as well. So what that gives us is kind of we're closer to the actual operation in some of those tests to see, for example, how the bending stiffness changes when we put on different tensile loads. One of the questions, of course, is how well does the rig kind of replicate what we're asking it to do. So that's just one example here on the headstock, and replicating angles for slightly different control parameters. So you can see it's following the angle very nicely, but actually if you look at the time series here, you can see some of the speeds as well, and some of the wave groups actually from that numerical simulation. So that we have to kind of set up some of those controls every time we run the rig. So it's very much tailor-made to whatever the component sample is, because both axes, it's also a coupled system. However the cable responds will affect how the rig operates. So one of the primary reasons why we do that is actually in this plot here, and that's one of the few that is published and which I can show, but you get something similar for every cable type for testing. And it's really the hysteretic behavior and what's called the stick-slip behavior of those cables. So you have the curvature on the y-axis and the kind of the ratio of the bending moments on the y-axis, and the slope of those curves is effectively the bending stiffness of that cable that's been under test here. The red line, so that straight line, is usually what you would put into things like Orcoflex as the bending stiffness for the cable. So that's the assumption, and you can see that it's actually quite a way off of what's happening in reality. It's an approximation, so around the core, yes, you get the general slope correct, but actually there's some hysteretic behavior. So what happens with the cable is if you load it, it'll have a linear response, which then becomes non-linear. So that's where it slips. And then if you unload it, it does that in reverse. So there's some hysteresis at the center there, and it matters also the magnitude of bending moments and tension matters on the size of that hysteresis. So that's one of the, I guess, valuable contributions of the physical testing, that you get a better understanding of what is the actual load response of the cable compared to the simplified one. I've got one example here on which we worked as part of the Marionette projects with NSW cable and CPNL, and that was for offshore fixed wind and basically the scouring problem that some of those early installations have experienced, in where if you have the original seabed, these are static cables, so you'd have the cable coming out the J tube and a very short section going into the seabed, so that you minimize the free span. Over time, you had there's some global scour, and in cases quite a lot of local scour. So in this example here, you can see that the free span grows quite dramatically, which basically leaves the cable exposed to both wave and tidal currents, effectively swinging the cable from side to side. And each of those is basically a load cycle that the static cable shouldn't experience. So a lot of those cables over time have failed, and there's some reporting in the press on those as well. And that's largely where some of those insurance claim and the cable failure rates I've shown earlier, where some of those are coming from. The test we've done is on the back of a numerical model to estimate kind of what is the maximum axial force that cable sees coming out the J tube with that increased free span, and what's the maximum bending moment it experiences as well. And we've tested kind of the combined system of the cable and the bend restrictors. So these are our split pipe bend restrictors. And we've put those in the rig to basically apply both the tension and the bending moment to that assembly, to see firstly if those split pipes are kind of retrofitted onto those existing cables, is it able to protect it, but also to see what is the cable response to the overall loading. One kind of specific task here was, I think they had different suppliers for those shells. So we had a 3D scan before, we tested them, and a 3D scan afterwards, for us to basically work out what is the wear at different positions in that string, but also how do the different suppliers compare. And you can see kind of comparing the tailstock and the headstock. Overall, kind of there's an average wear here, but overall the higher wear is near the headstock, as you'd expect. That's where the motion is. But you can see quite a difference between the different suppliers as well. So you probably go for supplier C in this case, which has the smallest wear. There should be a video for it as well. So this is kind of what we call a regular accelerated test. So each of those swoops is basically one full tidal cycle, swinging the cable from one side to the other. So we were trying to replicate about 60,000 cycles to basically replicate what is the what are these cables likely to see over time. And one of the conclusions was that whilst the cable bend restrictor provides some additional integrity to the cable, it still allows it to move. So one of the conclusions was that actually those cables at the end will have some fretting and some wear inside them, because although you reduce the amount of movement, there still is movement. We've also tested kind of different assemblies, so that was also as part of Marionette's program. That was quite a nice test from a science perspective, because it's not something that you'd normally do under, say, strictly commercial conditions. So that was work between Hellenic Cables and with CRP Subsea, which used to be Trelleborg. So Hellenic Cables obviously manufacturing the cable, and then CRP Subsea producing or specifying some of those bend stiffener ancillaries. So we've run a test kind of the same cable without the bend stiffener, and then the very same profile with the bend stiffener, to be able to quantify what is the effect of the bend stiffener. Can we, because these are also designed with numerical models, but it's always difficult to actually validate that against the physical realities. So we've done two extended tests on those, and you can see the setup here. So because the bending moments were quite high, we added a component here to basically protect our linear actuator. And then you can basically see the connection here, the headstock, that's without the bend stiffener, and then another cable with the bend stiffener in position. I'll show you some of the results. So it's in terms of the test, basically the same, cyclic loading side to side with different tensions applied. And you can see here, so that's over time with different tensions applied. So 40, 60, and 80 kilonewton tensile loads at the same kind of bending cycles. And you can see kind of the cable with the bend stiffener overall sees a lot less displacement and maintains those cycles a lot better. Where that's better to, so this is in kind of showing you the displacement in the what we call the z-axis. But what's actually better to see is for a regular, so we've given it a bending angle of 3.7 degrees and then measured the bending moment at the same time. And for those cycles, you can see with and without the bend stiffener. So if you've only got the cable, the test rig basically has to afford just about less than 10 kilonewton meters to reach the 3.7 degrees. Once the bend stiffener is fitted, that goes up to about 15 kilonewton meters. So you can really quantify kind of the contribution that the bend stiffener makes. This one's displacement controlled, so we're pushing it to those angles. And these were kind of the early tests just to see what I always refer to as the performance. That's the performance testing. What can you see for kind of individual cycles? And then we've carried on to do kind of a repeated test, and I've got some slides for that as well in a moment. But the main question there is, how do those systems degrade over time? So that's really asking the fatigue question. And for some of those load sequences that we've run, if it's only the cable between the first and the last cycle, there was quite a lot of degradation for the different, certainly for the low tensile ones, and we didn't need as much a bending moment in the end. So the bending moment we had to afford was dropping off. Whereas for the one with the bend stiffener A, we need a much higher kind of bending moment, and we could see some of the degradation in the bend stiffener, but still higher bending moments required compared to the cable on its own. So the bend stiffener over time, yes, gives a little, but still maintains some of that performance, if you like. And that's the result here in terms of times rather than number of cycles, because that's obviously the confidential bit. But the point is, the cable alone kind of failed fairly early, so you could see it slipping. Then it went. So that was for 4 degrees at 80 kilonewtons, whereas the bend stiffener actually maintained its performance for quite a long while, and then started slipping, but still hang on fairly well, and then failed at the very end. But you can see if you just count across, so it's kind of factor 4 increased cycle life with the bend stiffener fixed, or with the bend stiffener in place. And then in terms of bending moments, and I think that's quite an informative plot here as well. So again, the cable on its own, as that fails fairly early, but you can see how rapidly kind of the performance of the cable in terms of bending moment resistant, or in terms of bending resistance, drops off. So what was 10 kilonewton meters early on really becomes rather small towards the end. So that's again displacement control. So we're asking the rig to go to 4 degrees, but basically it needs a lot less force towards the end because the cable's been worked in. Whereas with the bend stiffener in place, you can see that we're kind of consistently above the 10 kilonewton meters that the rig needs to afford to push the cable over. Those spikes here, I should say, is when we stop and start the testing. So when we start off, there's slightly higher bending moments until it's kind of back in regular cycling. So these were kind of a couple of examples, and really I hope it showed that kind of the physical testing and the dynamic testing of those cables serves a range of purposes. So there's not a one test fulfills them all. We've done tests where almost the question is only what are the cable properties, and that could be basically a test of a few days where we establish all the bending stiffness and the actual stiffness of the cable. And that's still important because these properties can then go, say, into the numerical models or be used as quality assurance for what the kind of the design envelope was for those cables. So that's an important step, and actually doesn't need that much test time and effort. What's more effort, and we've done a few of those over the years, is to investigate the different cable failure modes and how they interact with ancillaries. Again, you can do a performance test, and I've showed some of the slides where there's not so much test time involved. Yes, a little bit setting up and running those, but actually the actual net test can be fairly short. Whereas as soon as you go into kind of fatigue testing and cable testing, you're looking at 1 million cycles. SIGRA stipulates 1.5 million cycles. So you'd be looking at tens, if not hundreds of days of testing. So that takes a long time. And we've done that for some projects. I've got a video here. So for the Floatant project, we've done a fatigue test. From a test perspective, these are actually pretty boring because you come to the test rig day in, day out, and you push a button and it does that. So you just run a lot of cycles. Having said that, well, it's a bit cheek and tongue to say these are boring, because these tests are really important to really understand, well, what is the fatigue limit of those cables? How many cycles can we trust them? What is the degradation over time? So they are important tests, but they need both time and obviously significant resource to fund a longer test campaign. What's also important, and I think that's looking towards floating wind, is if those cables go into new environments, you ideally want to test what you think they have to survive physically before you go anywhere near field installations. And we see some of that work coming through, really quantifying both the performance and the endurance of the cable. So with the test we're doing as part of Supergen, I said we're aiming to have some of those representative cable types, which basically aims at that first part to have a set of representative cable properties that improve some of the global and local modeling that we do in the cable design. Thank you very much for your attention. I hope you found it interesting. I'm not quite sure what's in the chats or how we run the discussion, but I'm sure we'll find a way. So very much looking forward to your questions and comments. Well, I found the chat. So here's one, two. Which one do we want to start on, Lee? Oh, that's you, Lee. Okay. Oh, so here's a question.
Yeah, there's a question.
I'll just read those out. Yeah, because I'm not sure everyone could see those. So I'll just read the questions out. So the question is there any estimate on the overall financial project impact of dynamic cable design on the wider development of offshore wind, I suppose, OW, given it is one of the major investment elements of an offshore wind site, especially how that will affect floating offshore wind? It's a barrier to targets that needs to be addressed. So what is needed to do from an R&D perspective, given the drive to floating offshore wind in the Celtic Sea? Well, I can give an answer on for fixed offshore wind, because I actually have some of those figures. So in terms of, and that's what's come out recently through some of the insurance reports and news. So in terms of overall capital investment, the cable infrastructure is somewhere between 10 and 20%, depending a little bit how far away you are, for sure. But typically, all the cabling is somewhere between 10 and 20% of your capital expenditure. And kind of the insurance concern then came because if you look at the claims, it's 80%. So in terms of, is the capex causing you any failures, or are the components causing you any failures? Cables were kind of overrepresented in that weighting. So it has a drastic impact. I think some of the issues are, and I'm not sure who's on the call, but that might be an interesting topic for discussion. I think when the projects are delivered, at the design stage and installation stage, they're very much driven from a capital expenditure point of view. So you want to keep the capex low, whilst obviously fulfilling all your requirements. But the focus is very much on capital expenditure. That comes at a trade-off with kind of operational, including failures, operational impacts. Because you could think of and some farms started doing that. You could think of, okay, let's have, if the cable is so critical, well, either invest more in the cable or have redundant cables, which will increase your capital expenditure. But operationally, you would have something to fall back on if your main cable goes. But so that's kind of the trade-off, and that's, I guess, what happens within the projects. For floating offshore wind, I think there is a realization that the cable will be much more exposed. So it'll be definitely dynamic cables. A rough figure in terms of costing between static and dynamic cables, without violating anything, is roughly a factor of 10. So you pay roughly 10 times as much for a dynamic cable than you pay for a static cable. And again, the same questions are there. Is one enough? Do you trust that one cable? Have you qualified it to a degree that you can trust one cable, or do you need redundant ones? Because if your cable breaks, that has a massive revenue impact on your project. There's a little distinction here between the inter-array cables and the export cable. When the export cable fails, that's obviously worst case scenario because your entire farm is offline. One inter-array cable, you could say, is not a problem. If multiple inter-array cables starts to fail, then you have a problem. So it's definitely a thing that needs, or one of the critical components that need work, and I would argue need more qualification work, and recognition in the design. So I think the other important part is to have an integrated design between the mooring and the cable, rather than seeing them in isolation. But it's, again, it might be a function of stakeholders, because I'm not aware of a company that offers cables and mooring systems and could therefore do an integrated design. You'll be a site developer and you'll ask one company for moorings and you'll ask another one for cables. So they need to work at their interface. I hope that's an answer.
I just sort of jumping in there. I think you're right. Just to follow up on that, I think given that it is a challenging thing with the floating side of things, and cables are going to be clear about that. The floating offshore wind farms are going to be 60 kilometers plus out at sea, and plus 80 meters of water. The cables seem to be a very important part, and it just is there a thinking about a new design of the cables, how you do that so you ensure not necessarily the export one, because that's the more important one. Maybe the array cables aren't so much of an issue, but do you think there is something which is, that's coming along from the research side saying, well, actually, these cables are going to be coming onshore at the next point, but they need to be at a certain level above from the fixed side of things?
Yeah, I mean, on the export cable side, you could argue that kind of the way they're installed that's well known. The challenge is that the subsea cables, because the arrays grow, the voltage levels go. So that the voltage level increased from 66 kV to they're now looking at 132 kilovolt designs.
Yeah.
So already you're introducing some innovation to a new type of cable. So you need to requalify all of that. In terms of designs, there's lots of different ideas. And there's two schools of thought. So you can have the cable very dynamic and actually allow it to move and make it survive that. Or you can make it very stiff, very heavy, and basically say we don't want that cable to move at all, which means when it does move, you have issues. So there's different schools of design. It is, and that is one of the challenges. I think it is very site specific and also kind of floating platform specific. So all the different platforms have different constraints, and which is why I talked a little bit about the couplet modeling as well.
Yeah.
Because it's things like the excursion of the platform will determine what the cable has to survive. So it's then almost, if you fix your cable design, you have to make a mooring design that accommodates it. But primarily you'd make the mooring design to stabilize the platform. So you kind of have competing design objectives a lot of the time. But
I'm no electrical
more qualification. I mean, for floating wind,
but on the connection side, from the connection side, just like I say, I'm no electrical engineer. But from the connection side, when that comes ashore, if you've got new designs of cables and so on that's hooking into the grid effectively, does that make a difference? Are they on board with these new designs, or?
Yeah, I mean, on the electrical side, they obviously then they need to have the higher voltage substations as well.
Yeah.
It's more, I think, rather than a reliability issue on the grid side, is more of a capacity issue, really, that the grids are there. So if you would build out Celtic Sea in the next 5 years, you wouldn't have the grid to accommodate it. So you'd have nothing to connect to. But that's a different talk. That might be one.
No, I agree. It's just interesting. It's like that. There's that much power coming back. Where's it going to go to? That was my question.
Just looking at the chat. Any other questions you can see? There's one new one.
Yeah, there's someone from
Jinyu Wang from. I just read it out.
Yep.
Hi Jinyu, from Ori Catapult. He says thanks. So his question is, what do you think is the most vulnerable component for a dynamic cable? And what do you think is the most vulnerable auxiliary part? Is it a good idea to have a sacrificial auxiliary part that can be changed more frequently? So I think I talked briefly about the vulnerable elements. And I can, if I find the slide, but I can talk about it. So it's basically 3 areas in terms of vulnerability: hang-off point, or just below the bend stiffener section, so close to the hang-off point. And then if it is a lazy wave configuration, near those flotation buoys, and then the touchline point. It's really those that things go wrong with. And then any joints you have. So that's kind of the areas to look at. In terms of auxiliary parts, I think the challenge is that, again, you need to qualify the auxiliary part in conjunction with the cable, because they're not separate. So I don't think so much the issue will be that, say, your bend stiffener fails. What will fail is the connecting mechanism between the bend stiffener and the cable. Or if you look at flotation parts, I know they're looking at pressures and kind of do they disintegrate almost so the integrity of the buoyancy module itself. But I think that the more important issue is your attachment mechanism, is that reliable enough to sustain 10, 20 years? Do you need to kind of is it a good idea to swap them or have sacrificial ones? Well, I mean, as a reliability engineer, I believe in redundancy, but that comes at cost always. So that's always a trade-off. In terms of changing things, I would argue that there's two different schools of thoughts, and that's if you know your design life and you schedule those in, you can go with changing things, but any intervention will also cause a cost and disruption. So I think the other school of thought is no, let's build it for 20 years and we don't want to touch it. But that might not be possible for some of the sites if you just have too many cycles. But it's an important question, because that could say the industry would settle and say, okay, we actually agree, and we'll have, again, is it capex driven, or are you happy to spend some opex? You could reduce some of the capex and shift it into the opex if you say, okay, let's, sake of the argument, we'll change the cable after 5 years. Let's say the dynamic part. That would reduce some of the specifications for the dynamic section of the cable, but you'd have a massive operation to swap that part, and any intervention also always has the risk of making things worse from a kind of maintenance point of view. So yeah, I haven't got an easy answer.
Yeah,
I think it's the answer there.
Yeah, thank you, Philip.
It depends on context. But yeah, I believe almost having those, and that's why I showed those two, having those interface tests is important, because you can qualify the bend stiffener on his own, but actually what you need to be in that service simulation realm is to have that attached to the cable with some realistic loads.
Yeah, totally agree with you at this point. Yeah, thank you, Philip.
Because it's almost cascading failures. So say the attachments, and it's understanding those failure mechanisms. So say the attachment of, I don't know, sake of the argument, the buoyancy module. Parts of your buoyancy modules stay intact but lose attachment, or fall off the cable, or move along the cable to change the shape. That means you now have a different load regime on the cable that it hasn't been designed for. Yeah. And then that overloads the cable, and so on and so forth. So what's not a straightforward failure could actually be quite a big impact on the cable life itself.
Yeah, thank you for your answer. Yeah, for the first question, I think I'll just maybe make it not very clear. I was mentioning about the different layers of the cables, for example, like insulations, and because for the dynamic cable, we are now focusing on the internal sliding and the internal frictions between layers. I mean, what do you think is the most vulnerable part of, for example, as a conductor or insulation or some other layers like a sheathing or metallic screens?
Yeah, probably all of those. Yeah, I mean the metallic sheath is exposed, definitely, and it depends a little bit on cable construction what's the most vulnerable part. But I mean, one leads to the other. So if the metallic sheath fails, your insulation will break down. So that may well be the first layer in trouble. But similarly, say it's not the most vulnerable, and say it's the armoring.
Yeah.
If the armoring fails, your cable will still be working for a while, but then all the loads will be that much amplified on the different layers that very soon afterwards, so the sheath will also go. So I think the answer is none of those layers is allowed to. They all have to survive. So you rely on all of those layers to survive. But I mean, it's coming down almost to engineering some of the basic principles, because on the bending stress, and a lot of focus is on the conductor, but actually the conductor's in the center, or close to the center at least.
Mm-hmm.
So they'll see some of the lowest bending stresses just by sheer, you're in the center, like second moment of area. Whereas the conductors and everything, the further out, will see higher bending stresses, which is one of the challenges. Just if you look at the outer diameters, if you go to higher voltages, which is the drive, well, you need more insulation. You need a larger cable. Larger cable, higher bending stress.
Mm-hmm. Yeah.
So again, almost competing design objectives. You could build a more dynamic cable at lower voltage levels, but then you're not meeting the voltage levels for the 15 plus megawatt turbines.
Yeah, I think. Sorry, I want to add another question. Is
Yes, please.
I've saw you. You have presented really good result comparing the cable with and without band stiffener, and I just wondering, have you been tested the cable with single armoring or double armoring? The result could be interesting. And also for the cable with or without the sheathing, because for some metallic, for some dynamic cable manufacturers, they are promoting the cable without metal sheathing, like a wet design. Is this in your planned testing in the future, or?
So, like I say, so we tested lots of different cables with kind of all the different features. Lots of armoring, not so much of armoring. Different wet or dry designs. But there'll always be single projects. So we can't, almost from the science point of view, we can't say, here's all those cables lined up. This is how they compare. So we're trying to do that for the Supergen representative cables.
Okay.
Yeah, because as you know, every one of those cross sections is kept fairly confidential.
Yeah, lots of confidential issues. Yeah, because we are from our couples, me and also my manager Alvaro also attend the meeting, and we are planning to build like a failure mode database. But we have made a lot of confidential issues that some of data cannot be disclosed. Yeah, so do you have any suggestion on that, or maybe are you willing to contribute to this database as well, and we could work together on that?
Yeah, I think is it the electrode database?
Yeah.
You're trying, or is it a different one?
Yeah, electro is one of the I think Charlotte is here. Yeah.
Yeah, hi there.
Hi Charlotte.
How are you doing? Great presentation. I just wanted to jump in there to say that it wouldn't be the electrode database that you'd be feeding into. We're working on something slightly different, which is looking at a sort of universal FMECA that we could use across a number of different projects and to support stakeholders. So it's a slightly different project, but ultimately it's the same idea of trying to get as much information as possible to the wider industry.
Yeah, no, happy to be involved. Also, I think I think I'll be at the new site in Aberdeen in June at some stage. So it'd be good to see your test facilities as well.
Yeah,
there's definitely not enough test capacities or test facilities. So I think there's some work we can definitely do together. There's more chats. Oh, have you got time for one more question, Lee?
Yep, go ahead. Last question.
So Edvaldo, also from the ORE catapult. So besides tensile bending fatigue, do you see other potential failure modes that might occur during cabled installation or operation, torsion, VIV, buckling? Yeah, all of those. It depends a little bit on the phase. So lots of things went wrong in the early days of installation. And that's largely exceeding minimum bending radius or exceeding axial tensions during the pull-in. VIV is more an issue, I think, when we go to deeper waters and very stiff cables. But yeah, all of those need to be assessed. I mean, and need to be modeled as well. Torsion, if that's correctly designed, that shouldn't be an issue. So they usually the dynamic cables will be torque balanced. So you shouldn't have too many torsion issues, unless, of course, the hang-off isn't correct. Then you have issues there as well. And yeah, generally you need to avoid compression for all of those cables. Well, I think that's all the questions from the chat. Thanks for all the interesting discussions. It looks like the Supergen Hub and the Catapult will do some cable work together, which would be great. And yeah, do sign up to any future webinars, or indeed look out for, I guess, what will be the representative cables at the end of it, once we've completed some of the testing and kind of come up with a representative design that doesn't step on anyone's toes. So thank you for your interest, and yeah, there's still lots of work to do in cables. So I'm sure we will have a few more years of R&D work ahead of us. Thank you very much, and have a good afternoon.
Thanks, everyone.